Okay, so gases. They're literally everywhere, all around us. But have you ever stopped to think about what they really are? I mean, down at the molecular level, it's just complete chaos. So how in the world do scientists manage to find any kind of order in all that madness? Well, that's where this really clever idea comes into play, the ideal gas law.
Yeah, let's just start right there with that big question. What is a gas exactly? We breathe it in every second, we pump it into our tires, but what's actually going on inside all of that space that just looks empty to us? What's so cool about this is that the guy who actually coined the word gas, a 17th century chemist named J.B. van Helmont, he totally got it. He actually based the word gas on the Flemish word for chaos. And honestly, as we're about to see, that description is way more accurate than he probably ever imagined.
All right, so let's dive right in. Let's embrace that chaos. What is actually happening down there at the microscopic level?
So picture this. Inside any gas, you've got this enormous number of molecules, and they are super far apart from each other. And they're not just sitting there, they are zipping around at incredible speeds, just bouncing and colliding completely at random. That's the reason a gas expands to fill up whatever container you put it in. And because they're so spread out, the forces between them, well, they're basically negligible. It's just this wild, chaotic dance of tiny little particles. Okay, so how can you possibly predict what something that chaotic is going to do, right? Well, the answer is a really brilliant scientific shortcut. Instead of trying to model all that chaos perfectly, which would be impossible, scientists decided to just invent a simplified version. And they called this concept an ideal gas. Now, this isn't a real gas, it's hypothetical, a kind of perfect model. And to make it work, we have to make a couple of big assumptions. First, we pretend the molecules themselves take up zero space, and second, we pretend there are absolutely no forces pulling them together. I know, it's a simplification, but it turns out to be an incredibly useful one. Here's a great way to think about it. Just imagine a giant 3D pool table, and it's filled with billions and billions of tiny little billiard balls, all moving super fast, bouncing off each other, bouncing off the walls, but, and this is key, they never ever stick together. That is our ideal gas. So now that we have this simplified model, we can actually describe its behavior with a single, really elegant equation. And this, right here, is the heart of it all, the ideal gas law. But hang on, before we jump into the equation itself, we have to deal with a little problem. How do we count the molecules? I mean, we're talking about astronomical numbers here. You can't just count them one by one, right? So, scientists came up with a special unit for this, and it's called the mole. So 1 mole of anything contains, well, this many molecules. This is Avogadro's number. That is 602 with 21 zeros after it. It's just a mind-bogglingly huge number, but it gives us a way to work on a more human scale when we're dealing with atoms and molecules. And that brings us to this beautiful equation, PV equals nRT. It looks so simple, doesn't it? But it is a revolutionary piece of science. What it does is connect 4 key properties of a gas. You've got P for pressure, V for volume, N for the amount of gas, that's our moles, and T for its absolute temperature. And yeah, we have to use an absolute temperature scale, like Kelvin, because it starts at true zero, the point where molecules literally stop moving. It just keeps the math nice and clean. So yeah, this one simple formula ties it all together. That R in the middle, that's a special number called the universal gas constant. You can kind of think of it as the magic ingredient that makes the whole relationship work for pretty much any gas. It's the key that connects the big picture stuff we can actually measure, like pressure and volume, to that invisible, chaotic world of molecules. Okay, so that's all the theory, but how does this actually play out in the real world? Let's put this law to the test, shall we? All right, here's a perfect everyday example. Have you ever noticed that the pressure in your bike or car tires seems higher on a really hot day? Well, the ideal gas law explains exactly why that happens. Let's break this down. See, inside your tire, the volume of the tire and the amount of air you put in it, they're pretty much constant, right? So according to our law, that means pressure is directly tied to temperature. As the day gets hotter, the air molecules inside the tire start moving faster and faster. They're hitting the inside walls of the tire harder and more often, and boom, the pressure goes up. The math here shows that for a pretty normal temperature increase, the pressure goes up by about 6%. The law predicts reality, and it does it perfectly. So the ideal gas law it's an amazing tool, but we have to remember it's an approximation, it's a simplification. So the big question is, when does our simple, ideal model start to fall apart? Well, the model works so well because, under normal conditions, gas molecules are really far apart. But what happens if you crank the pressure way up, or you drop the temperature way down? See, in the real world, molecules do take up a little bit of space, and they do have these weak little attractive forces between them. So when you squeeze them really close together with high pressure, or slow them down with low temperatures, those two little details suddenly start to matter a lot. And that's when a real gas stops behaving ideally.
And to account for that, scientists came up with more sophisticated models. The most famous one is called the van der Waals equation. You can think of it like the sequel to the ideal gas law. It's a bit more complex because it adds in these little correction factors for the volume of the molecules and those forces between them.
And this more complex model can predict something that the simple ideal law just can't: phase changes. At really low temperatures, the van der Waals equation can actually predict the exact point where a gas will condense and turn into a liquid. Our simple ideal gas law with those perfect little billiard balls that never stick together, it has no way of predicting that at all.
But look, even though it's not perfect, the ideal gas law is still a total triumph of scientific modeling. It takes the absolute chaos of trillions upon trillions of bouncing molecules, and it boils it all down to one simple, elegant, predictable relationship. Its power comes from its simplicity.
And that really leaves us with a final thought to chew on. Think about it. From economic forecasts to predicting traffic jams, we rely on simplified models like this all the time to make sense of a really complex world. The ideal gas law is just one fantastic example, but it kind of makes you wonder, right? What other ideal models, what other perfect approximations are we using every single day to shape our understanding of, well, everything?